Hey there, math fans. I'm Dr. Andy Lovelace. I'm doing this little series on the history of pi and some facts about pi with Pi Day approaching. As I said before, many of my students, I realize, have celebrated Pi Day for many years in their elementary, middle, and high school classes, but never really know what it is. So I'm going to give a little bit of history. I don't know if this will help very much. I'm going to give the history from the perspective of a stop sign. I just want to give a little bit of a sense of how pi was originally approximated. How we do it now is we use infinite series, and there's lots of good ways, and we have calculators. But the original way was fairly simple. We were going to put a polynomial inside and find the perimeter of the polynomial, the polygon, find the perimeter of the polygon, and then use that as an approximation. And Archimedes is the one that's attributed with this. Now, Archimedes did not have trig. He didn't have sine and cosine of tangent, so he had to do everything just reasoning things out from right triangles. He did have the Pythagorean theorem. I was going to make a video going through what he did, but I realized it has complications, and there are many resources out there like that, and I'm just going to give you an idea, but then that got me thinking, well, what's a polygon that everyone knows? So here on the right is the stop sign. So if you can kind of make out the circle in there, the circle almost fits on the border of that stop sign. There's this little white border on the edge of the stop sign. Not quite perfectly. You can see it kind of goes over the red slightly, but you probably could convince yourself that the length of the circle is going to be somewhere between the perimeter of the outer edge of the sign around the white border, which would be an overestimate, and the perimeter of the inner red octagon. So let me show you those real quickly. So here's some points. There's the inner one. There's the outer one. Let's connect them. Ooh. Ah. So what I'm going to do is find the perimeter of the red polygon and the perimeter of the green polygon. And what I'm going to say is, hey, the length around the edge of the circle is going to be between those two. Now, typically we use a circle of radius 1. I'm using a circle of radius 15. Why am I doing that? Stop signs in the United States have a standardized length from side to side of 30. And so there are other sizes, but the radius is 15. So I'm going to find the perimeter of a stop sign. You're going to have to think about this video every time you go to a stop sign. I do a lot of things like this for my students. I'm like, here's how you're going to have to always think about this. So don't watch my video about how I use toilet paper to find the surface area of a cylinder, because then you have to think about math every time you go to the bathroom. So you don't want that to happen. Anyways, in doing this, I looked up stop signs from around the world because I was wondering if they were all octagons, and I found this one in Bhutan that's actually a hexagon, and I'll show that one in a second. Here's the hexagon one, which is actually where Archimedes started. I don't think Archimedes started with a stop sign, because I don't know if stop signs existed at the time. So I've been saying that I'm going to do something that Archimedes never did. And it's not going to be a good approximation. But the principles of what we do, I will show you, involve just basic trigonometry. This is not like something... Now, what Archimedes did at the time with no trigonometry is impressive, but we can understand how to find the perimeter of a polygon. That is not beyond you. You can do it. So I'm kind of presenting this to everyone. Okay, so what I would like to do is label a few things, and then we'll work from there. So I'm going to put a few little lines in here. Those lines have names. So the line that goes... And maybe I should get rid of everything else. So right now I'm just looking at the interior piece that I have. Okay, so let's say a couple things about that. And the exterior one goes all the way out to 15. Maybe I'll show that one first. Apologies here for some. That's actually the stop sign, the outer edge of the white part of the stop sign. So that's 30 to 30. So if we can find that green perimeter, it's going to be bigger. And I've actually turned it here. I don't know why I turned it on the left. But anyways, we know the length from the center to the edge. That has a name. So that length from the center to the edge. And again, I think I had a reason to turn it. Now I'm thinking that I don't. But from here to where it touches right there is called the apothem. I'd never really thought about that till many years after I'd been studying math, that even has a name. I turned it because I was trying to line it up with this. I know that, so I'll show you a little bit of, I really like making these visuals. That does not change the perimeter. I hope you understand. Okay. So anyways, that's what we call the apothem. And that for this one is going to be 15. So we have, I'm doing this one first. This is not quite what I originally had in mind. You don't plan these things? That's why we don't watch them to the end. All right. And then this length to an actual point is called the circumradius. So if you haven't heard these, if you're going to study polygons, apothem, I believe, is that one. I'm probably saying it wrong. And then we have this R, which we call the circumradius. I don't know what that is yet. Circumradius. And then the last thing would be the side length. So we'll have S be the side length. And that's actually what we're trying to find if you think about it. If we can find the length of one side, we can multiply it times 8. The other thing I guess we might want is the number of sides. 8 sides. So a game plan here. Our game plan is we know the apothem and we want to know the perimeter. And let's put a little game plan here. Perimeter equals 8 times S. If our goal is to approximate pi, we could then divide that by the diameter. Because pi is, if you watch my previous video, circumference. So you could divide this by the diameter, which is 30 in our example. And this will be approximately pi. It'll be a terrible approximation. But this will give you the idea. And then the whole idea is you could do it if there were more than 8 sides. It's actually a very slow approximation. I'll talk about this at the end, that you need quite a few sides before it starts to get good. But at this point, we've now entered a little bit of trigonometry. Again, Archimedes didn't have this, so we're at the advantage that we have taken algebra trigonometry. Okay, so let's look at this. It's basically just a little triangle problem. So here's this little triangle. So right now I'm looking at a triangle that looks like this. We have this length. The apothem is 15. And that makes a right triangle. And if you've taken some trig, you know that right triangles are pretty nice to work with because you can do all that. I didn't learn until I was a teacher what SOHCAHTOA was because I'd never been taught that. But I've heard students say that all the time. So we have this thing. The other side, this side is going to be S over 2. My S's look like 5s. I apologize. But S is how far it is for the side length. So right now I'm just pretending we're looking at one side. And we know that 15. The other thing is this R. And the moment we start to think about that, we go, well, the only thing I don't really normally label or don't have is that angle. But I do have the angle. So why do I have the angle? And we're going to do it without radians. I feel like it's funny to use radians, but we're going to cut this up. This is a pizza. We're going to cut this up, and this is the standard way to study polygons, is to break it into triangles. How many triangles are there? There's 8. If it's 360 degrees all the way around, you can divide it by 8. So that's the next little piece of the puzzle. That little angle there is going to be 360 divided by 8 divided by 2. So normally we label this angle, and that's going to be 360 divided by 8, which I think is 45 degrees. If I want this little angle, it's theta over 2. It's half of it, which I think is, so theta over 2 is 22.5. And then the rest of the problem is a little bit of trig. And right now we're doing the one where we have the apothem goes all the way to the edge, that picture on the right. So I'm finding the perimeter of that. So our goal is to find S. So it's just a little exercise in trigonometry. S is the opposite side. I know the adjacent side. So which trig function will get us there fastest? Tangent. So that's how this goes. Just a little track through the fact that I know the angle because I'm breaking it into equal parts. That's a common strategy with trig. And then I know the ratio. So we're going to write, make sure I can still see it, tangent of 22.5 degrees is equal to opposite, which is S. I know my S's look like 5s over 2 divided by 15. And I should say that so many students don't know how to do this because they have some rules about flipping fractions they were taught. And I jokingly have been telling students, stop memorizing your flipping rules because it sounds like I'm saying something inappropriate. But I don't try to ever flip a fraction. I just think about what it is. I jokingly say, here's the big bar. Let's multiply top and bottom by 2. Well, that will cancel this 2, and I get S over 30. So I never flip anything because just because of years of teaching, I've seen students flip things, get it wrong, and they don't know what to do. They don't have any other way to think through it. So I've started to believe that we should just tell them multiply top and bottom by the same thing. So that's something you can see completely in any situation is right. So this is going to be S over 30. Okay, so when all is said and done, what am I getting? What is this S? It's 30 times tangent of 22.5. Now I'm going to do something that Archimedes couldn't do and cheat, but Archimedes didn't have stop signs. Okay, so I'm doing 30 tangent of 22.5. I'm going to make sure I'm in degree mode. 12.4. So this all together, the side length, which maybe I can put here, is 12.4264 inches. Now, if you search online for the side length of a stop sign, a lot of times when this comes up in problems, people use 12. There are signs of that have different apothem, different lengths. But if you take a standard large stop sign, it's 30 inches from side to side, which means the side length is 12.4 to this number. Anyways, if you multiply that times 8, I've got my calculator here, I'm computing, I get 99. So an interesting thing about a stop sign is it's about 99 inches all the way around. So this here all together, I know I'm squishing it all together, but this is, let's get rid of pi for a second. So what I'm getting is that the perimeter is 99.41 inches. So now about 100 inches to walk around a stop sign. I thought that was kind of interesting. If you divide by 30, which is the diameter of the circle, let's see, I'm using my calculator wrong. Dividing by 30, I get the following. So this approximation all the way around, if you find that perimeter and divide by 30, which is the diameter, you get this approximation. That pi, and I can see that pi is definitely smaller than this, 3.3137. A terrible approximation as promised. But that gives you the idea. It also shows you a few things that the 30s are basically going to cancel. It's going to be 8 times all this stuff. And you could start to see, so let's erase a few things. You can start to see an approximation method forming. What we just figured out is that pi is less than this thing. So the 30s will cancel. The 8 was our n, so it's n times tangent of whatever that angle was. And what was that angle? That angle is what we got when we took 360 divided by n and then divided by 2. So 360 over 2n. And it's never written that way in a book. It's written as 180 over n. And there's an upper bound for pi. Now Archimedes didn't write that because he didn't have tangent. But there we have an upper bound. We know pi is smaller than that. You could plug in larger and larger numbers. It's fairly slow. Let's do one in here. Let's do 96 sides. I'll talk about why in a second. I'm doing tangent 96 times tangent of 180 divided by 96. So I just did this with 96 sided polygon, tangent of 180 over 96, and I got it's 3.1427146. That's notable because that's the approximation that Archimedes got. And then he approximated that with a fraction. He was like, what's a fraction that's really close to that? And he used 22 over 7. 22 over 7 is slightly larger than this. So from this, he said, okay, this is smaller than 22 over 7, which is a fairly small denominator, which we kind of like. Let's get rid of this. Sorry, I know this is already too long and everyone's already asleep. But this is 3.142857, which is slightly larger than that. So from this, Archimedes was able to say, all right, that's less than 22 over 7. And that basically from then on, and that was really a miraculous that he was able to get without trig to 96-sided polygon using his little recurrence method, all by hand without a calculator. And this is really the approximation that lived on for a long time as the best approximation. Okay, I thought I would add something here, which is, well, what if we wanted a lower bound? So we just found that we went around the outer edge of the stop sign. What if we go around the inner edge? So the inner edge would be this one, these points. Let's get rid of the outer ones. Let's get rid of that. And we would like to know the perimeter of the red one. Now the one I'm doing is actually slightly inside the inner edge. I'm actually using the one that touches. These points that touch along the edge are called roots of unity. And if you want, I have a separate video where I talk about how the roots of unity saved my dad's life. So if you want to check that out. So here we have a new one, and we could think about what has changed. We can play the trig game again. So in this situation, what do we know? We don't know the apothem, but we do know the circumradius. So we know that this is 15. How does that change things? A little exercise in trig. So we're going to draw this same little right triangle. This now is 15. This is now s over 2. This is the apothem. And we have this angle, this 22.5. Now which trig function do we want? Nice little exercise in trig. For students taking trig, they can understand the thought process of approximating pi by using basic trig ideas. So this 22.5 we already found. We would like to deal with the opposite in the hypotenuse. That's sine. So you can say sine of 22.5 is equal to s over 2 over 15. And now we have it. And that length around the outside, that perimeter, so let's get rid of that. It's going to be the exact same setup. You're going to do the number of sides times whatever the side length is. And then if you want to approximate pi, you'll divide by 30. That's about pi. This will be an underestimate. And that's really a math. It's kind of nice when we get an over-underestimate because then we can have confidence where our answer is. Okay, so this implies that the side length is 30 times sine of 22.5. So we put that here, and when all is said and done, so well, I won't do the smaller calculation. I'll just do our approximation of pi. So if I did 8 times sine of 22.5, the side length is sine, 30. I was going to do 30 times sine of 22.5. I get that it's 11.48 inches. So this was 12.42 inches. This is 11.48 inches. That makes sense that it's smaller side length. If I multiply that times 8, it's about 91 inches to go around that thing. If I divide that by 30, I get the following. This is approximately 3.0614. Again, a terrible under approximation. But that completes a picture of this. So we're going to go here. Apologies, do a quick little jaunt over. We'll move this over a bit more. And then we have our final result. That this is n sine of 180 over n. And this, this gives you a good enough way to approximate pi. It's just n has to be pretty big. So what we learned is that pi, for our numbers for a stop sign, we learned that pi is between 0. This and the other one I think was 3.41. Let me recalculate that. 8 tangent of 180 over 8. That was 3.31. So here we go. Archimedes didn't have a stop sign, but pi is between those two things. Terrible under approximation. Interestingly, what Archimedes did is he started with a hexagon because the side lengths are nicer. Like we can actually say what they are without trig. And so you could use that Bhutan stop sign and find the links here. Let me make this 6. Ooh, it's turned a little bit. Let's line her up. Where are you at? You don't have to make sound effects, but you could do that to approximate our circle. Anyways, so I'll say a bit here. It was interesting to look at stop signs around the world, but I'm going to show you a little bit of history. Okay, so Archimedes' estimate was this. So there's using the hexagon, and that actually gives, you can do that trig if you want. It gives you nice lengths for those pieces. Okay, but it's a terrible approximation. The reason he used that is because then he doubled. So if you don't have all the trig stuff, you could then try to find, what he did is he proved a recurrence. He said there's a connection between that one and what happens if we double. So if you double the number of points, you can see that it shares some sides, and you can draw a little, kind of looks like a kite here shape. And you can find a relationship between the length of the black little piece, if you just sort of zoom in here, and you can find plenty of these derivations online. But there's a relationship between the length of the two black lines here and the length of the side length. And if you can find that relationship, it gives you a recurrence, meaning a connection between how to get double. And so that's how he did it without trig. All right, but there's complications. There's lots of trig. Whenever you get into a trig problem with lots of triangles, it's always a question of what's the cleanest way to do it. So I just, rather than, as I said, I originally thought, oh, I'll do this. I just pulled it up. This is from Wolfram Alpha. Not Wolfram Alpha. This is from Wolfram, people that make Mathematica. So they said, well, you can actually give a recurrence for this. Now, looking at this makes it seem complicated, but you can see that formula right here. Now, they're using pi instead of 180. They're using 2 because, oh, that's just one side. So anyways, that's what they got. And then they said, well, we want to multiply this. This is the side. The total perimeter is this. And then this formula is the connection between the black lengths and the other side lengths. It says if you want to know the length of a side for the next one, the doubled, there's this connection between them. And from this, he could say, well, I know the side length for 6. They're nice numbers. And so I know the side length for 12. And so then I know the side length for 24. I know the side length for 48. I know the side length for 96. And he figured all that out with precise calculations, no calculator. And got this. So I didn't make this. I pulled this from one of the many. So he did, all right, it's not great for those. You can see with 6. Our example with a stop sign is only slightly better than that, right? So that was 3 and 3.46, you can see. Oops. Let's make this a little bigger. So then he did it again with 12-sided. Again, that wasn't a great approximation. 24-sided. He started to be able to prove that it was 3.14. 48-sided. I imagine he thought, dang it, I got to 48 and it's still only this good. Man. And so he went a little further, 96, and he was like, well, that gives me 2 digits and I'm tired. That's my guess. And then he saw that that second one actually could be written as a fraction with a really small denominator as 22/7 or something close to it. It's a terrible approximation in the sense that we say this converges slowly, because even at 96, you're not that close in terms of your 2 digits. So you have to go to 96 to get to 2 digits. How many would you have to go to get to 4 or 8 or whatever? So this is kind of a slow process, which is why people were interested in this. So beyond this, the next step was to do infinite series, and then we had calculators. So things sort of changed. So last thing to finish up this history was, here's from Wikipedia, sort of the number of digits over time. So you can see, people used the number 3 for a long time. And then later we got to like 10 digits and then more. And this is kind of the time of Archimedes. And then it pretty was plateaued to about 12 digits for a couple centuries. And then the 1600s, a lot of math is starting to take off, calculus and things like that. So this kind of ties in with the advancements in math. 1700s, it bumps up a little bit, over 100 digits. 1900s, beginning of the 1900s, we are about 1,000 digits. And then, 1950s, we have calculators, computers start to come into play. Because of that, the methods change to using infinite series. There's even all sorts of unusual methods people have been in. And now the number of digits is just basically as high as we can store it. I think many quintillion or something. There's not much value in that, except for the fact that it's interesting, the methods themselves. Okay, hope that was interesting. I think that hopefully is a little better than my first go around. But history of pi through a stop sign. Thanks for listening.